51 kiloohms can be written as 5-1 with 3 zeros. 5 is green, 1 is brown, and 3 is orange. 6.8 kiloohms can be written as 6-8 with 2 zeros. 6 is blue, 8 is gray, and 2 is red. 470 ohms can be written as 4-7 with 1 zero. 4 is yellow, 7 is purple, and 1 is brown. Finally, 1.8 megaohms can be written as 1-8 with 5 zeros. 1 is brown, 8 is gray, and 5 is green. That wasn't too hard, was it? Let's now discuss some of the idiosyncrasies of the 4-band resistor color code. Using the system as illustrated up to this point, it's impossible to represent any resistor value less than 10 ohms. It is for this reason the colors gold and silver are occasionally employed in the 3rd band. Gold in the 3rd band means multiply the first two numbers by 0.1, whereas silver in the 3rd band means multiply the first two numbers by 0.01. Consider this set of two resistors with the following color code in the first 3 bands: brown, black, gold; green, blue, silver. Brown is 1, black is 0. Gold means multiply 1 0 times 0.1. 1 0 times 0.1 equals 1 ohm. Green is 5, blue is 6. Silver means multiply 5/6 times 0.01. 5/6 times 0.01 equals 0.560, or more appropriately, 560 milliohms. All right, that was pretty fun. Are we ready to move on to the secret 4th band? No, I must test you. For the first set of resistors on the left, interpret the first 3 bands and express the resistance value using proper engineering format. For the second set of resistors on the right, determine the colors of the first 3 bands. Did you write the color code down or commit it to memory like I asked? If not, here it is again, and do what I told you to do. Write it down or commit it to memory. You are on your own now. Again, for the first set of resistors on the left, interpret the first 3 bands of the resistor color code and express the resistance value using proper engineering format. And for the second set of resistors on the right, determine the colors in the first 3 bands. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Let's take a look at the first set. Yellow, orange, yellow means 4, 3, followed by 4 zeros, or 430,000, or more appropriately, 430 kiloohms. Brown, blue, black means 1, 6, followed by 0 zeros, or 16 ohms. Orange, white, orange is 3, 9, followed by 3 zeros, or 39,000, or more appropriately, 39 kiloohms. Finally, brown, orange, gold is 1, 3 times 0.1, or 1.3 ohms. Let's now take a look at the second set. 2.4 megaohms is 2, 4, followed by 5 zeros. 2 is red, 4 is yellow, 5 is green. 620 milliohms is 0.62, which is 62 times 0.01. 6 is blue, red is 2, and multiplication by 0.01 is silver. 4.7 kiloohms is 4, 7, followed by 2 zeros. 4 is yellow, 7 is purple, and 2 is red. Finally, 620 ohms is 6, 2, followed by 1 0. 6 is blue, 2 is red, and 1 is brown. I must reiterate, the 3rd band is the most important band. Let's say you required a 620 ohm resistor to oppose the current established by a voltage source and accidentally put a 620 milliohm resistor in its place. Say goodbye to whatever you're hooking up, because it's going to go up in smoke. Pay attention to the 3rd band and double and triple check your work in low light conditions. True story. I had a student who was colorblind, and I guess there's different levels of colorblindness, but he was like stage 5, life-threateningly colorblind. What's crazy is I never knew he was colorblind until the 2nd quarter of his 2nd year. I have no idea how he did this, but he never had a problem with the resistor color code. He basically taught himself through the course of his life that different shades of gray meant different colors. I was pretty impressed by this. If this dude can do it, you can do it too. I don't know about your lab partner though. I think they're a lost cause. All right, I know you've been sitting on the edge of your seat this whole time waiting for me to tell you what the 4th band means, and here it is. The 4th band is the tolerance of the resistor. No, this does not mean the resistor values positive performance regardless of race, gender, class, sexual orientation, or color vision. This means that the resistor was manufactured at a certain level of precision. The robot slaves that manufactured these resistors are given certain resistance values and are not punished if they manufacture something that is close to the desired value. This level of closeness is indicated by the tolerance rating. This is the space where the gold and silver bands typically go. A resistor with a gold band is manufactured to plus or minus 5% of its nominal or nameplate value, and a resistor with a silver band is manufactured to plus or minus 10% of its nominal or nameplate value. Think about it. Gold is customarily considered a more valuable metal than silver, therefore something with a gold rating is better, or manufactured to tighter standards, than something with a silver rating. If you ever find a resistor with only 3 bands on it, it means the manufacturer is so embarrassed about their level of precision that they just skip mention of it altogether. This is kind of how I feel about U.S. foreign policy from 19 March 2003 onward. It's not that it was a bad idea. It's that it was a terribly awful idea executed appallingly poorly. A resistor with only 3 bands means it has a plus or minus 20% tolerance. If you run across a resistor with only 3 bands, go get another one and pretend it never happened. Numerically, tolerance means you can find a resistor with greater or lesser resistive values than the nominal or nameplate value. For example, consider a nominal 750 ohm resistor with plus or minus 5% tolerance. This means an actual resistor might be 5% less or 5% greater than 750 ohms. The easiest way to calculate this range is to take the nominal value times 0.95. That's something 5% less than 100%, and then the nominal value times 1.05, where that's something 5% greater than 100%. Therefore, a resistor with a 750 nominal value could have a bottom range of 712.5 ohms and a top range of 787.5 ohms. Now, before you get all up in the robot slave's face for making such a shoddy 750 ohm resistor, stop to consider the next highest and the next lowest resistor in the standard resistor set. You don't need to memorize the standard resistor set, but you will over the course of the time learn it. Basically, not every size of resistor is made, and there's a funny numerical sequence that occurs for a reason. The next lowest resistor in the standard set is 680 ohms, and the next highest resistor is 820 ohms. Now, consider the range offered by 680 and 820 ohm resistors manufactured with a plus or minus 5% tolerance. A nominal 680 ohm resistor with plus or minus 5% tolerance could be anywhere from 646 ohms to 714 ohms, whereas a nominal 820 ohm resistor with a plus or minus 5% tolerance could be anywhere from 779 ohms to 861 ohms. Do you see what's going on here? The tolerance is there for a reason. There's a degree of overlap between the 680, 750, and the 820 ohm resistors. Just by being choosy about which resistor you grab from a roll, you basically have a complete, unbroken spread of resistive values. Regarding component tolerances and lab practices, do the calculations for your expected observations using the value of components you are actually using. There's no sense in plugging in 750 ohms if your 750 ohm resistor actually has a resistance value of 712.5 ohms. Do the calculations first, and don't be surprised by this stuff. I don't think we need to spend much more time on the topic of tolerance, besides a reminder that you should not judge your lab partner by their race, gender, class, sexual orientation, or color seeing ability, but rather by their ability to assemble a functional circuit with the correct components. All right, that's all I've got for you for this lecture. Final note about the color code is this: use it. Don't just use it for checking your lab partner's shoddy work. Use it for wires. The circuits you're building are going to get real complicated real quick. And if every wire in your circuit is the same shade of red, this is a recipe for disaster. Assign each point of connection a number. Anything connected to node 0 gets a black wire. Anything connected to node 1 gets a brown wire, and so on. The point is, there's an existing standard, and you may as well make use of it to simplify troubleshooting. In conclusion, this lecture took a look at the 4-band resistor color code. We learned the colors represent numbers, and the bands represent resistive values, multipliers, and tolerances. You should be able to interpret the value of an unknown resistor employing the resistor color code, and be able to identify the color code of a known resistor. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you use the correct components. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.